Hello everyone, this is Professor Robert Solis. Welcome to this video lesson. What I want to talk about today is algorithm efficiency. It may very well be that you come up with an algorithm of how to solve a particular problem. The question is if whether or not that algorithm is efficient. So what we'll do is let's just create a program that will determine the running sum. But I'll have three versions, algorithm A, B, and C, of how we can determine what the running sum is based on the user input. Okay. So the first thing that we'll do is in the declarations, I don't know if the user wants to enter a huge number. So I'm going to create a long, and a long is a 64-bit whole number. So it's a huge number. In fact, let's see here, if I do a quick search, and let's see here, C++ long data type. So let's see what's, well, in terms of a long integer, if it were unsigned, it would go from 0 to, okay, so let's see here, that's million, billion, trillion, septillion. I forgot what the next number is. Is that quintillion or something like that? That's a huge number if this were unsigned. If this were signed, then it would be plus or minus half of this, going both directions. So it's a big, a big whole number. Because I don't know what the user number wants in terms of obtaining the running sum. Give me the running sum from 1 to 1 billion. Gosh, that's got to be a huge number. So I'll create a long to accommodate that. And then if I'm going to do that, then it would also make sense to go ahead and create a variable called running sum that actually is going to contain what is 1 plus 2 plus 3 plus 4 plus 5 to whatever the user number is. Well, the next thing that I'm going to do then is to get the user input. So we'll say cout, enter a whole number. So I'm asking the user to enter a number that does not have a decimal point, and we'll put that right into the variable user number. Now in terms of the calculation, let me create three algorithms. So this one over here I'll say is algorithm A. I want to copy and paste this. And so the idea is to create three different algorithms that generate a running sum. Some of these are going to be efficient, some of them are not. So let's take a look at a very straightforward way of determining the running sum. And so what I'll do is I'll say, let's let the running sum first of all start off at 0. And I will use a for loop. And again, I have no idea how many iterations this thing needs to go through. It really is dependent on the user input. The user may say, I would like to get the running sum from 1 to 1 trillion. I want to be able to accommodate that. So what I'll do is I'll again create a long counter that I'll just simply say is I. Okay, so we'll start that off at 1. And as long as I is less than or equal to the user number, then we'll just simply say I++. Okay, and so in order to determine the running sum, that's just simply the running sum is going to be assigned the running sum plus I. So in other words, I will be 1. And then I is going to be 2, and so 2 is less than the user number, say for example, so what's 1 plus 2? And then I is going to be 3, so let me say I had 1 plus 2, which is 2, and then plus 3, that's going to be 5, and then 5 plus 4 is 9, and then 9 plus 5 is 14, and so forth and so on, right? So this is just very simple algorithm for determining the running sum. All right, and then in terms, we'll skip algorithm B and C for right now, we'll just jump over here to the output. And for the output, we'll just simply say cout the running sum from 1 2, and then whatever the number happens to be that was entered by the user number. So we'll say user num is, and then we'll submit whatever that answer is. running sum. And we'll go to the beginning of the next line. Now I want to be able to see what that looks like, so I'll say system pause. And of course, you know that this only works on the Windows operating system. Okay, let's start off with a small number. So I'll run the program. Hopefully everything builds successfully. Looks like it did. Let me increase the font size so that students in the back of the classroom can see that. So we'll go to 28 points. There you go. And there's our program right there. All right, enter a whole number. All right, so let me just do 5. That was pretty quick, right? 1 plus 2 plus 3 plus 4 plus 5. What is that? Well, let's see. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 5 plus 10 is 15. Okay, so that works. Now, let's see what happens if I enter 1,000. That was pretty quick, right? 500,000. Let's see what happens if I enter 1,000,000. So 1, 2, 3, 4, 5, 6 zeros. Again, pretty quick. Let's see what happens if I enter 1,000,000,000. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's taking a little bit longer now. Okay, so you saw that there was a little bit of a delay in terms of how long this is taking. And of course, you can understand that the bigger the number, the longer this is going to take to be able, because we're doing this 1 plus 2 plus 3 plus 4 plus 5, this looping structure until we get to the actual user number. Okay, so this is one way of solving the problem of creating a running sum. Okay. Now, let me show you another way. So what I'm going to do is I'm going to comment this chunk of the code right here, and I'll just simply comment that out. And I'll go over here to algorithm B, and let's describe another way of how we can generate the running sum. So once again, I'll assign running sum to 0. We'll do another for loop, and we'll say as long as this counter I will start it off at 1, and as long as I is less than or equal to the user num, and then I++. I think over here I did long. Maybe I should be consistent over here and let's type in long again, because again, I don't know how big the user number is, so I want to be able to accommodate that. Now, this works. It's not an efficient way, but this does work of putting another for loop within here. I'll create another counter called j. J will start at 1, and as long as j is less than or equal to I, then we will increment j. And what we're going to do in here is we're going to say the running sum is going to be assigned whatever the old running sum is plus 1. So this is another way of basically doing the 1 plus 2 plus 3, so forth and so on. But I'm using a nested loop. So you know how this works. This is like an outer loop, and this is an inner loop. So there's going to be a time where we're going to go outer, inner, outer, inner, so forth and so on. Okay. And I guess if I wanted to be consistent with what I have above, assuming that the user number is going to be really big, I could put a long over here as well. Okay. Everything else can stay the same. All right, well, let's see how this algorithm works. So I'll start the program. And let me move this over here, and I want you to be able to see the code. Here it is. And let's see, let's start off with 5. Again, pretty quick, right, in terms of being able to determine the running sum. Run the program again. Let's enter 1,000. Okay, I did notice it was a little slower, just a tiny bit slower, but it gave us the right answer. Run the program again. And let's enter 1,000,000. 1, 2, 3, 4, 5, 6. Enter. Wow. So this algorithm, especially compared to the other one that we had, algorithm A, is taking a little bit longer. Now, it is running. Let me prove that to you. Let me go back over here and not stop, but pause the program. It looks like The running sum so far is this. I is 10,000 something and j is 4,000 something. Let me go ahead and click continue. And again, this thing is iterating and it's still trying to solve. And we're going through an outer loop and through an inner loop. And again, let me pause the program and show you up. See, those values are changing. And we are slowly getting to the running sum, but you can see that this algorithm is not very efficient. So if you were to choose between the two of these, obviously algorithm A would be the better one because it's more efficient. So in computer science, it's not only about will this solve the problem, it's will this solve the problem efficiently. And whenever you are doing nested loops like this, you now know that that can be very inefficient. If you had one loop, that's obviously going to be something that's going to be operating at a little faster rate. If you are doing a nested loop, it's almost like this behaves like an x squared, like an exponential amount of time, as opposed to maybe a linear growth, which is a singular loop, say for example. Okay. So we're still going in this thing. It's still taking time to solve. So you know what? I'm not going to wait. I'm impatient. So I'm going to go ahead and stop debugging and immediately go to algorithm C to share with you yet a different way of solving this problem. So let me comment out these lines of code temporarily and go over here to algorithm C. Algorithm C is one line of code. Running sum is going to be assigned whatever the user number is times user num plus 1, and that entire quantity is going to be divided by 2. So I don't know if you knew this or not. For those of you who took my CS232 class, one of the things that we do is, number theory. Like how do you get, is there a formula to determine the running sum, or is there a formula for Pascal numbers or for factorials or what have you? That formula right there is a quick formula for determining the running sum. All we do is we take the user number times the user number plus 1, we divide the whole thing by 2. So let's see what happens now with this algorithm. So I'm going to run it. And I'll move this up over here, move this down here so we can see what's going on. All right, you know that 5 works, and you know that 1,000 works. Let's see what happens with 1,000,000. 1, 2, 3, 4, 5, 6. Bam! That was quick. Let's do this again. How about 1,000,000,000? 1, 2, 3, 4, 5, 6, 7, 8, 9. Bam! That was quick. Trillion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Bam! That was really quick. All right, so in other words, by far, this is the most efficient algorithm. So the lesson for you is, if you can, stay away from the nested loops. I mean, if time efficiency is of the most important, dealing with huge numbers. If you're dealing with, smaller numbers, I don't know what that means. It could be 1,000,000 in a particular case. It could be 1,000. It could be 1,000,000,000. Or whatever. It just depends on the situation you're dealing with. But if you can stay away from the nested loop, this seems to be one of the most inefficient ways of solving a problem. In terms of a single loop, that's a little bit more efficient. And then in terms of an equation, that by far is the most efficient way to solve the problem. And so we've seen this as a result of this very simple running sum algorithm, 3 different algorithms to determine the running sum. Now, in the textbook, this graph is made available for you. So some algorithms have this log base 2n type of behavior. And that is really good, especially when you are dealing with large numbers, with large data sets, right? Then you can see here how this thing just kind of levels out and it doesn't really grow very much. These type of algorithms, they're terrible. 2 to the n, look how sharp this thing goes up, right? So this is over here, value of growth function. And over here, n represents like the number of iterations. So this thing is going to take a huge amount of time to solve. Problems with n to the third are a little bit faster. N to the second are a little bit faster. N right here, you can think of that as a constant growth. And then there are some algorithms that have a log 2 base N type of functionality that seem to be very, very efficient. Okay, so this is a table that's in your textbook that kind of illustrates, depending on the type of data that you're working with, you want to make sure that you pick an efficient algorithm. If you're dealing with small data sets, then it's not that big of a deal. But for larger data sets, this can be very, very crucial. And so we call this growth rate. And what happens is computer scientists use this type of notation, call it the big O, to describe what is the order in terms of the order of efficiency for your particular algorithm. Now, if it happens to be that, say for example, I have a nested loop, and maybe I have a constant formula, and I also have like 3 nested loops, say for example, that make up my particular algorithm. Notice that all of this can be reduced to just simply whatever the one that offers the most inefficient, which in this case it looks like n to the 3 power, right? Because if we have n to the 3, you can see that that's less efficient than n squared, which is over here, and that's less efficient than maybe like a constant value. So if while you're solving your equation, you have a nested loop, you can think about that as n squared. You have a 3 deep nested loop, you can think about that as n cubed, right? So you're trying to determine the efficiency of your algorithm, just take the one with the highest exponent, and that pretty much defines the efficiency of your particular algorithm. And so now you can tell your boss, well, the reason why it's taking so long is because our algorithm is kind of inefficient. And it may very well be that you have no other choice but to work with this particular inefficient algorithm. But at least you understand how, if possible, to make this thing more efficient. Try to stay away from nested loops. Try to stay away from nested loops. See if you can work with the direct equation at all times, because that will give you the greatest amount of algorithm efficiency. That is it. So this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.